This video entails a hypothesis which seeks to provide reasoning that the strong force is not a fundamental force, but is fundamentally electromagnetic in nature. Argued herein, perhaps a type or types of electromagnetic bonding between protons and electrons is at the heart of what is described as the strong force, the neutron itself being a form of electromagnetic proton-electron bond/union. I want to begin this talk with some relevant background, accompanied with some intermittent soft hypotheses, which together converge and lead to a comprehensive and fundamental hypothesis. Let's begin. With regard to multi-proton nuclei, it is interesting that such nuclei are never observed to be devoid of neutrons. Additionally, it appears that certain specific quantities of nuclear neutrons correspond with the particular quantity of protons within multi-proton nuclei. These observations might suggest that something about the neutron serves an integral role in nuclear stability. Perhaps the radioactive decay processes of beta- decay and electron capture may provide some insight into this role of the nuclear neutron. Generally occurring in neutron-rich nuclei, beta- decay is a type of radioactive decay whereby an electron is emitted from an atomic nucleus. The result is an increase in the atomic number, the number of protons, of the nucleus by 1, at the expense of the reduction of the amount of neutrons of the nucleus by 1, while the mass number remains constant. Effectively, a nuclear neutron becomes a nuclear proton as an electron is emitted from the nucleus. The decay of a free neutron into a proton and an electron is also considered an example of beta- decay. Electron capture is a type of decay process whereby a proton-rich nucleus captures/absorbs one of the inner atomic orbital electrons, resulting in a nuclear proton becoming a nuclear neutron. Interestingly, the mass of a neutron is very nearly equivalent to the mass sum of a proton and an electron. The mass sum of the proton and the electron effectively being equivalent to the mass of the neutron, along with such radioactive processes as beta- decay and electron capture, might indicate that the neutron is a kind of union/composite of the proton and the electron. Perhaps further insight can be obtained from the radial charge distribution data of a neutron, which demonstrates that the neutron is not completely/uniformly electrically neutral. The charge is positive very close to the center of the neutron, but with increasing radial distance from its center, the charge eventually becomes a net negative charge. With the outer boundaries of a neutron exhibiting a net negative charge, it would seem that there would naturally be an electrical affinity of neutrons towards positive particles such as the proton. Evidence also suggests that in terms of charge radius, the size of the neutron might be slightly less than the size of the proton. And when the radial charge distribution of the proton is superposed with that of the neutron, it appears that the positive charge peak of the neutron occurs at a radius which is less than the radius of which the proton's positive peak occurs. And this positive peak of the proton is greater than the positive peak of the neutron. As well, it appears that the net negative charge of the neutron begins at a radius which is less than the total radius of the proton. Combined with the evidence above, which seems to imply that the neutron is a composite of the proton and the electron, this data about the charge radius and the radial charge distributions of the proton and the neutron may further support this point and may suggest that the neutron is a type of bond/union between the proton and the electron, where the smaller charge radius of the neutron would be inferred to be the result of a type of overlap of its proton and its electron, where parts of the proton electric field and electron electric field mutually cancel, effectively decreasing the overall charge radius of this proton-electron system. The neutron positive charge peak occurring at a radius which is less than the radius of the proton positive charge peak, along with the neutron positive peak being less than the proton positive peak, might reaffirm such a proton-electron overlap, whereby the influence of the negative field encroaches/penetrates into the positive field, causing the neutron's maximum positivity to be lesser and to drop off at a smaller radius than that of a proton. Continuing with some more background and soft hypotheses, consider the following. For electron orbitals, there is a greater energy difference between consecutive energy levels when descending from higher energy levels to lower energy levels. If this trend continues, it might be the case that at the nuclear level, where it is proposed that protons and electrons are bonding, there is a greater difference in energy between that low energy level of such a bond and the next higher energy level compared to the difference in energy between any two consecutive electron orbital energy levels. To simplify, from higher to lower energy levels, there is an exponential increase in energy required to jump an electron from a lower energy level to a higher energy level. Generally speaking, this would imply that it would be exponentially more difficult in terms of energy required to jump electrons the closer they were to the nucleus. Now, if we also consider that as two charges, say a proton and an electron, get close enough together, the effective charge they experience from one another increases due to the shielding/screening effect dropping off to zero, then by extension, this may be an insight as to why there would be such a strong electromagnetic interaction between protons and electrons when they get close enough together. Due to a lack of electric field screening/shielding between one another, this increase in the effective charge mutually experienced by two charges at a given distance apart would mean that the actual strength of the electromagnetic force between the two charges would increase, which herein is hypothesized to be the true nature of the so-called strong force. Consequently, approaching very small distance scales of charge separation, it would seem that such an exponential increase in the electromagnetic force, along with an effective increase in the actual strength of the electromagnetic interaction between protons and electrons, would make asymptotic freedom a natural consequence. At this point of the talk, we have several seemingly interrelated soft hypotheses. A summarized hypothesis of everything in this talk so far is as follows. The processes of beta-minus decay and electron capture, as well as the neutron mass effectively being equivalent to the mass sum of a proton and an electron, along with the fact that a neutron on its own outside of a nucleus will decay into a proton and an electron, along with the superposed radial charge distribution data of the proton and the neutron indicating that the positive peak of the neutron is less than the positive peak of the proton. The positive peak of the neutron occurs at a radius which is less than the radius of which the proton's positive peak occurs, and the net negative charge of the neutron begins at a radius which is less than the total radius of the proton, all together seem to suggest that the neutron is a combinatory system of the proton and the electron. These, combined with the radial charge distribution data of the neutron indicating the neutron exhibits a net negative charge towards its outer limits, in conjunction with an exponential increase in energy required to jump a charge from a lower to higher energy level as the energy levels and effectively the charge's distance from the nucleus decrease, along with what would seem to be an effective increase in the actual strength of electromagnetism between a bonded proton and electron due to a lack of screening/shielding between them, in addition to the extreme instability and even non-existence of multiproton nuclei devoid of any neutrons, such as the diproton nucleus of helium-2 or the triproton nucleus of lithium-3, etc., as well as other nuclear instabilities unless certain amounts and perhaps also certain structural arrangements of neutrons are exhibited for a particular element, all together seem to further suggest that it is fundamentally the electric field, ultimately comprised of proton-electron unions/bonds, which manifests as the so-called strong force. Another soft hypothesis, which appears to have some relevance to this overall talk, is a hypothesis that the fine structure constant is the ratio of the Coulomb force and the strong force. While not complete hypothesis herein, it may be worth mentioning as something of intrigue and potential insight into future hypotheses. Some background and the argument for this soft hypothesis are as follows. The fine structure constant alpha is a unitless number which is approximately equivalent to 1 over 137. It is a measure of the strength of the electromagnetic force that governs how electrically charged elementary particles and light interact, and is known as a coupling constant for the electromagnetic force because of how the strength of the electromagnetic interaction is dependent on the energy scale. Effectively, the value of the fine structure constant can vary based on a change in energy scale. The value of the inverse of the fine structure constant is about 137, and the strong force is about 137 times stronger than electromagnetism. Perhaps this is not a coincidence. Mathematically, the fine structure constant is equivalent to q squared over 4 pi permittivity times 1 over ch bar, where q is elementary charge, permittivity is the vacuum permittivity, c is the speed of light in vacuum, h bar is reduced Planck's constant. Notice how if we take q squared over 4 pi permittivity with respect to r squared and ch bar with respect to r squared, the result is a ratio of the familiar Coulomb force to some other force, the ratio of these forces remaining equivalent to the fine structure constant. The value of ch bar over r squared would be about 137 times greater than q squared over 4 pi permittivity r squared, just as the strong force is about 137 times greater than the Coulomb force. Interestingly, if we look at the denominator of this ratio that is the fine structure constant, the value of the denominator being ch bar, we find that ch bar is suggestively equivalent to 1/4 times proton mass times proton radius times c squared. According to mainstream physics, the mass of a proton is the result of the strong force interaction energy. However, with the proton mass and proton radius naturally emerging from the fine structure constant, which is the electromagnetic coupling constant, It might be more suggestive that the strong force is not fundamental, but that such properties of the proton have an electromagnetic origin. The conclusions, as well as the fundamental hypothesis of this overall talk, are as follows. What appears to be going on at the short-range interactions at the nuclear level is an effectively stronger electromagnetic force in the form of proton-electron bonding via the electromagnetic interactions between the positive electric fields of protons and the negative electric fields of electrons. In summary, the hypothesis herein suggests that the so-called strong force is not itself a fundamental force, but is fundamentally the result of an effective increase in the strength of the electromagnetic force between protons and electrons at very low energy, where effectively distance scales, as well as effectively electric field screening/shielding between protons and electrons, decrease.